Today's lesson is going to be about Lewis structures. Lewis structures are named after Gilbert Lewis, who is the most famous chemist to never win the Nobel Prize. He never got the recognition he deserved for coining the term photon. Being a pioneer in acids, we really understand the most about acids now because of him. And he also came up with these little structures that we named after him. Now, what we're doing is we're going to take the different atoms and we're going to basically get an understanding of where the electrons are and which ones are bonded and which ones are non-bonded. Okay. Now there's going to be steps to do this. We want to first find the total number of valence electrons. If it is an ion, so if it has a charge, add an electron for every negative charge, and then subtract an electron for every positive charge. Now, then we will decide the central atom. That will be the least electronegative element. That one goes in the middle, except for hydrogen. Hydrogen never goes in the middle. And then we'll draw bonds. One bond is 2 electrons. We'll subtract the number of electrons used from the total in step 1. Step 3, assign the leftover electrons as lone pairs to the outside atoms. Subtract the electrons placed from the total in step 2. Remember, hydrogen never gets lone pairs of electrons. If necessary, assign any leftover electrons to the central atom. If the central atom has an octet or exceeds an octet, you are usually done, but we'll check for formal charge. If the central atom doesn't have an octet, we'll create multiple bonds. So that step number 4 is usually where students start to have trouble, and I will help you along. I will do the examples on a piece of paper. The first one we're going to do is going to be water. So if we take H2O, and what we'll do is we will decide, we're going to count up the number of valence electrons. So our valence electrons, there is 1, hydrogen has 1 valence electron, and then oxygen has 6. We can find that off the periodic table. Hydrogen is in the first group, and then oxygen is in group 16, or group 6A. So oxygen has 6. And then there are 2 hydrogens, so we're going to multiply 2 times 1. And so we have 8 total valence electrons. So we'll take oxygen, we will put it in the middle, because remember, hydrogen never goes on the outside. And then we'll put our hydrogens as far away apart, just like so. And then, far away apart as possible. Now this is a bonding unit, so we have to draw bonds. So we will draw a bond in between these 2. Now remember that one line equals 2 electrons. So that is 2 electrons here and 2 electrons here, makes a total of 4 that we just placed. So we're going to subtract 4 from our list, and so now we have 4 left. We're going to take these 4 electrons and we're going to place them in lone pairs. Now you should place them on the outside first. However, hydrogen never gets lone pairs. And this hydrogen can't get lone pairs either. So we have to put them on the middle. Okay? So now that's good enough for the first time you've ever seen a Lewis structure. But what is actually going to happen in the next lesson, I'm going to show you how that these lone pairs are actually going to push the bonds down, and we're going to get a bent shape. So this is how water should look. You should always write water in this shape. That's actually critically important for future videos, future lessons, and future units, is write it like this. So this one is preferred. Now let's take a look at Nh3 Ammonia. So this one's kind of similar to water, except now you have 3 hydrogens. So let's count the valence electrons here. Let's see, nitrogen has 5, and then hydrogen still has 1, so we're going to do 5 plus 3 times 1, and so we'll get 8 total valence electrons to play with. Again, we have 8. So nitrogen is in the middle. Hydrogen never goes on the outside. And we'll put hydrogens spaced equally around it. I kind of screwed that up. We're spacing them equally around them. And then so we'll place a bond in between them here. So I did 3 lines, so that is actually going to be 6 electrons. Remember, 2 electrons per bond. So that is 2 valence electrons left over. Now we're going to place electrons on the outside. However, we can't do that anymore because now we need to place electrons here. So that is what the shape will look like. Again, we want to make the shape look a little bit better. So hydrogen is typically either written like this to clean it up, or you could write it like this, because the lone pairs are going to repel the bonds a little bit more, and so they're going to bend that down. We'll get to the shapes a little bit later, but this one is the most preferred drawing. Okay, so now let's get to another one. CO2, carbon dioxide. Let's see, carbon has 4 valence electrons, oxygen has 6, and so there are 4 plus 2 times 6, and that will give us a total of, let's see, 12, oh, math is hard, 16 valence electrons, okay, and then, so, the least electronegative goes is placed first. Now, if it's not hydrogen, that's typically going to be the one on the left. Carbon is always in the middle, actually. So oxygen is on the outside, and so we'll place them out like that. Now, this is a bonding unit, so we are going to put at least 1 bond here and at least 1 bond here. So we place 2 bonds, so that's 2 electrons here, 2 electrons here, makes a total of 4 that we just placed. So we're going to subtract 4, and now we have 12 valence electrons. Now we're going to place these 12 on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So here we are. We notice how I did that. I placed them in pairs. What we're doing is we're placing lone pairs. Lone pairs are non-bonding pairs. They're non-bonding electrons. That's what's going on here. So I place them in pairs right here, and I put 2 here, or I put a lone pair of electrons here, and then I put a lone pair of electrons here, and then here, and then here, and then here, and here. The reason why you alternate is so that you're making sure that you space them out as well as you can. Now what we have to do is that we just placed all 12 electrons. We're going to subtract 12, and we get 0. So we have no more electrons left to place. We can't put them on anymore. Now we're going to check to see if they follow the octet rule. So this oxygen is got 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons around it. So it follows the octet rule. This oxygen is also following the octet rule because it looks the same. Now this carbon only has 1, 2, 3, 4. So it only has 4 electrons. It is not following the octet rule. So we need to try to see where we can find the most stable one. Is there any way we could get oxygen to keep some of its electrons, or at least share them, and give them to carbon? Yes. What we can do is that we can erase some of these, and then we can draw a multiple bond right here. these two electrons are now going to get bonded, and they're going to be a bonding pair. These two electrons are going to get bonded, and they're going to get a bonding pair. So now all of a sudden carbon has 1, 2, 3, 4, 5, 6, 7, 8. Now carbon is following the octet rule. Okay, this oxygen is still following the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. So the way, let's clean that up. The way it will look is it will look like this. And I angle my lone pairs so that they're as far apart as possible, because remember, electrons don't like each other. They're going to repel. So, and it looks kind of like that. That is carbon dioxide. That is the Lewis structure for carbon dioxide. You can tattoo that one on your forehead as well. You know, your forehead's probably getting a lot of ink on it. So let's take a look at another one. CH2O. Carbon's got 4, hydrogen's got 1, oxygen has 6. So we have 4 plus 2 times 1 plus 6. So 4 plus 2, that's 6. So that's 12 total valence electrons. Now, which one goes in the middle? You're right, it's the first one. Okay? Except for hydrogen. Remember, hydrogen never goes in the middle. And then we'll place the other ones, the hydrogen and the oxygen, we'll place those around it. So we're going to put the oxygen on here, and then we're going to put the hydrogen here and the hydrogen here, as far apart as possible. We're going to draw at least one bond in between. And so we just placed 3 bonds, so that's 6 electrons. So we'll subtract 6. And here we are. Now we have 6 electrons left to place, so we place 1, 2, 3, 4, 5, 6. Remember, hydrogen can't accept lone pairs. That's a common mistake. You wouldn't be able to do that. Okay? That is right out. You may not put dots on hydrogen. Never, 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 never. Okay. So now we check to see if they follow the octet rule. Oxygen is following the octet rule. Hydrogen is following the duet rule. Hydrogen's following the duet rule, which is fine. And then, but carbon is not. So we're going to borrow some electrons here and make a multiple bond. So that would be C double bonded, just like that. That is the simplest ketone you can have. If you've heard of ketosis before, or the keto diet, you were trying to make ketones, just like that. That's what a ketone is. All right. And let's take HCN. That is hydrogen cyanide. So there's 1 hydrogen, there's 4 carbons, and then there are 5 valence electrons here. So there are 1 plus 4 plus 5 is 10 valence electrons. So carbon always goes in the middle. Carbon is the backbone of life. And then we have hydrogen and nitrogen spaced as far apart as possible. We'll place a bond in between each one. So you can probably see where I'm going with this. This is going to be 4. There were 4 here. So you have 6 valence electrons left. So we're going to put dots again. We have to put 6 dots. We can't put them on hydrogen, so we're going to put them all on nitrogen. Again, nitrogen is following the octet rule, but carbon is not. So again, you get multiple bonds again. So we'll have to erase those. And then we'll have to erase these. We got down to 0. I keep missing that step. And so we get that. So we get H, C, and then a triple bond to N. All right. So very cool. A couple of tips and tricks. Just remember, HONC. Let's see. So bonds. Hydrogen will typically form one bond. Oxygen will form two bonds. Nitrogen will form three bonds, and carbon will form four bonds. That is a very, very good rule. Okay? That is when they follow the octet rule, that's the way it works. Now, when it comes to lone pairs, hydrogen never gets lone pairs. Oxygen almost never gets lone pairs. Oxygen will get two lone pairs, and then nitrogen will get one lone pair. So that will help if you kind of want to get a very good rule of thumb. If you're that will get you through most of those structures. Now, let's talk about those dreaded exceptions, because exceptions like to find their way on the test. So exceptions happen because either you don't have enough valence electrons, or you had the possibility of d orbitals. You can check them out in your notes. So the first exception we'll take a look at is BeCl2. Well, beryllium is actually in the second group, so it only has two valence electrons. Chlorine has 7. So 2 plus 2 times 7 is 14. It's going to be 16 valence electrons. So we'll put Be in the middle, and we'll put chlorine on the outside, and draw a bond in between those. And so we just did 4 electrons, so that's going to be 12 valence electrons left. So that means we're going to place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Subtract 12, and we get 0. Now, that is actually totally correct. That is where you will stop. Beryllium does not follow the octet rule. Not follow the octet rule. That's because beryllium just has those two s electrons. It doesn't really have any other p electrons that it can bond with. So just beryllium only forms 2 bonds. 2 bonds. Just remember, beryllium has 2 bonds. BF3. Well, boron is kind of similar. Boron has 3 valence electrons, and then fluorine has 7. So 3 plus 3 times 7 is that's 21. 21 plus 3 is 24. So we're going to put boron in the middle. We're going to put fluorine on the outsides. We draw a bond in between them. Our bonds are a little wonky. There are 3 bonds, so that's 6 electrons. So 24 minus 6 is 18. We will place our electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Fluorine follows the octet rule, but boron does not. Okay? It does not follow the octet rule. Okay? So boron will typically only have 3 bonds. Carbon monoxide. This one is a really, really special one. You will get, I will just draw it like this. I will save you the pain. Carbon monoxide makes a triple bond here, and this is probably the only place that you will see lone pairs on carbon. That is very, very infrequent. PCl5. Now, phosphorus is in the 3rd row, so it actually has access to d orbitals. So this is going to allow it to get more than 8 electrons. So here we have phosphorus has 5 valence electrons, chlorine has 7. So 5 plus 5 times 7 is going to be 40. So phosphorus goes in the middle, and then chlorines are going to be spaced out around here. We're going to draw 5 bonds, and that was 10 valence electrons. So that is going to be a final total of 30. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So that is what phosphorus pentachloride looks like. Very cool. It does not follow the octet rule. Phosphorus can follow the octet rule, but it cannot follow the octet rule. It's one of those things that's kind of just takes practice. But PCl5 will look like that. And then one last one, sulfur hexafluoride. It is also similar, and you're going to get 6 fluorines around it. And it's going to, don't forget to draw those lone pairs. Remember, fluorine still follows the octet rule, but sulfur does not have to. So it's just phosphorus and sulfur are the only ones, and then boron and beryllium are really the only ones. I just threw in carbon monoxide because that one is a really special one. All right, so have a great day.